Hey everybody, Mr. Brooks here. So today we're going to talk about the last couple of sections for differential equations. So we're going to be talking about section 6.2, which is equilibrium solutions in the phase plane. And then our last lecture will be actually on 6.4, which is stability. So one thing I need to fix there. All right, so one important thing here is so we have talked about phase plane, and that's actually what this is. This whole section is getting more in-depth detail about what a phase plane is, and direction fields and how they're related to that. And then the next section, when we get into 6.4, is going to be talking about, well, it's important to know the behavior of our solutions because we want to know the behavior of our models, how they're reacting. And so we are going to get into that a little bit, talking about how a equilibrium solution could become stable, how it's what it means to be unstable, and what it also means to be asymptotically stable. And so that's what we're going to get into a little bit later. But for right now, we're going to talk about, I'm going to fix all these right now, what it means, what are equilibrium solutions. And we've seen this concept before. And then we're going to dive deeper into what a phase plane is and the direction fields are. All right, so first of all, we're going to talk about what an equilibrium solution is. So first, consider a system of autonomous differential equations. So again, just as a reminder what autonomous means, it means that these guys are functions that only involve y. So there is no t variable involved with these. And so we're dealing with n of them, so y sub n prime is equal to f sub n of y sub 1. Now again, this is notation that we've seen before. It's just a lot quicker to write instead of saying that it's got a piece of x or anything in front of that. So the nice thing is we can talk about systems of equations. So in vector terms, we're going to be dealing with y prime is equal to f of y. And so that's what type of functions we're dealing with. So again, when we bold, and again, I'm going to try to bold these, I'm talking about these represent vectors as well. So, well, now that we're dealing with the system, so we're going to define a new thing here. So we're going to let y sub e be a constant n by 1 vector such that f of y sub e is equal to 0. So when we plug in this vector, this constant vector, we're going to get zeros as our solutions for that. So that's what an equilibrium solution is. So a constant vector valued function, y sub t, which is equal to y sub e, on the interval from negative infinity to infinity. Let's write that out just slightly different. So again, we're talking about the t, even though we technically do not have t in our functions, but we're still going about the t-axis for this. This is called an equilibrium solution of the autonomous system. Okay, so let's go about real quickly. You can pause your video if you'd like. This is a real quick example to go through. So find the equilibrium solutions for the pendulum equation that we have here. So y1 prime is equal to y sub 2. y2 prime is equal to negative g over L. So that's going to be the length of the pendulum, g's gravity, sine of y sub 1. So our solution here, we're going to rewrite this just so that way we can get this in terms of our vectors. So here y is equal to y1, y2, and f sub y, when we plug it in, are our functions, y sub 2, negative g over L, sine of y sub 1. All right. In order for y sub f sub y to equal 0, all right, if we want to get the 0 vector out of this, or get zeros out, We need y2 to be 0, so y2 has to be 0. And y1, since it's built into sine, we want sine to go to 0, so y1 is going to be of the form m pi. So where m is either equal to 0, plus or minus 1, plus or minus 2, and so forth. So if we throw in some integer value in, we are going to get 0 in for sine, and so this will zero out our f sub y, which is what we want in order to find an equilibrium solution. Thus, the equilibrium solution solutions are y sub m of t is equal to m pi and 0. Again, y2 we wanted to be 0, y1 we wanted to be some integer multiple of pi. All right? So in this particular case, so again, that's very quick what we went through. So in this particular case, the constant solutions of the pendulum equations have a very simple interpretation. For even values of m, this represents the pendulum is at rest, and is positioned so that it hangs downward. So you can think of it as like a clock, and this is just going to be hanging down. So if we had some pivot point, and then here's the pendulum, some mass on it. All right. For odd values of m, the pendulum is still at rest, but is positioned in a vertically upward position. So then our picture would look like this. So to kind of give a glimpse of what we'd be looking at 6.4, so when we talk about stability of equilibrium here, if I barely push this second scenario, if I tap on this pendulum, all of a sudden it's going to take off and start swinging back and forth. So there's, with just a little bit of disruption, then all of a sudden we see this big deviation away from the equilibrium point. Likewise, if I do that same amount of disturbance on the first case, it's going to swing back and forth just a little bit, but then it's going to return back to normal, and there wasn't much deviation that occurred in this movement. So that's the idea of stability that's going to take place in the next section. All right. So now we're going to get into, well, how do these things look? So two-dimensional autonomous solutions are systems and the faceplate. All right. So here we are going to consider, again, we're going to look at just a two-equation system. All right. So the behavior of the solution system can be described and studied graphically. So this is what we're going to investigate here. So solution trajectories, which we have seen before in sections 4.5 through 4.7, most specifically 4.7, are plotted in a two-dimensional setting known as a phase plane. All right, where in this particular phase plane we can view the solution components as a parameterized curve in the y1, y2 plane. And again, parameterization, if you want to look back in your calculus notes, or if you do have this Stewart edition of calculus, it's in chapter 10 when we talk about parameterization and drawing curves in terms of parameterized with the variable t. Okay, all right, so we call this plane y1, y2 the phase plane. All right, so consider the following IVP, where a is equal to -1, -6, 6, -1, and we have initial value points 0, t is equal to 0, and 1, 0 are our particular variables. All right, so in this particular case, let's look at a solution. All right, so first of all, we need to take the determinant of a minus lambda I, and we're going to get negative, oh, I forgot to subtract my lambdas from this, so let me fix that real quick. Yeah. It's the beauty of this, we can quickly erase and go back. All right, this is equal to -1 minus lambda, the quantity squared, plus 36. We need to set that equal to 0 because this is the eigenvalue problem. And once you solve this, you're going to find out that lambda is equal to -1 plus or minus 6i. All right. Now we've seen before where we only have to find the solution to one of these guys because we end up with about the similar solution that might just be a constant multiple difference between the two. So I'm going to look at lambda is equal to -1 plus 6i. All right. When we plug it into our matrix, we're going to get -6i minus 6, 6, -6i. And again, multiplied by the vector, sorry, that's x1, x2, and this is all equal to the 0 vector. All right, so one note here that the second row is just an I multiple of the first row. So R2 is equal to I row 1. So this implies that we are just dealing with this system here of -6i, -6, and 0, 0 here. So this will help speed along our calculation. All right. Once we multiply this in, we're going to get -6i x1 minus 6x2 is equal to 0. Solving that, we're going to find out that x2 is equal to -ix. So x of 1. So that means for any choice of x1 that we do, we can figure out what x2 is. And so I'm going to say it's 1, and therefore x2 has to be equal to -i. Again, just plugging up this simple formula. All right. So now that we have that, we need to find our solution. So y sub t is equal to e to the -1 plus 6i to the t times our eigenvector, which is 1, -i. All right. Using Euler's equation, or Euler's formula, we're going to get -t times cosine of 6t plus I sine of 6t multiplied by our vector again. All right, when multiplying that, we are going to get the following. E to the -t cosine of 6t plus I sine. Whoops, I forgot my e. I to the -t sine of 6t. And then at the bottom, we're going to get -i e to the -t cosine of 6t plus e to the -t sine of 6t. Splitting it up into its real imaginary parts, we're going to find u and v, which will then be our solutions. So our imaginary parts are e to the negative t cosine of 6t, e to the negative t sine of 6t. Again, looking at the top, getting its real part. Looking at the bottom equation, its real part plus I. And then these imaginary parts, e to the t negative t sine of 6t and negative e to the negative t cosine of 6t. Now we're going to solve this. All right, our initial value is t is equal to 0. So if we plug in t is equal to 0, sorry, let me write down the general equation. So that way we have it. We're going to get e to the negative t cosine of 6t, e to the negative t sine of 6t. Again, this is our u and v. U and v. E to the negative t sine of 6t, and then negative e to the negative t cosine of 6t. Multiply by c1 and c2. Now when we look for our initial value problem, I'm going to plug in t is equal to 0, so we're going to get the matrix 1, 0, 0, negative 1, times c1, c2, and this is going to be equal to our initial value point of 1, 0. Therefore, c1 has to equal 0, and negative c1 has to equal 1, and c2 is equal to 0. Thus, our particular solution, our solution to this IVP, is the following. E to the negative t cosine of 6t, and then e to the negative t sine of 6t. All right. So let's look at the phase plane trajectory of this guy. All right. So one neat thing about this is with this multiple of e to the negative t, as t increases, as we move along the t-axis, if you will, if we were looking at a three-dimensional shape, this would be actually a spiral or screw shape to it. As t increases, these values of cosine and sine are going to be multiplied by a smaller and smaller value. So therefore, these values are going to be decreasing towards the origin. All right. So let's look at the phase plane trajectory. All right. So here I am going to look at a quick table of values. Here's y1, here's y2. And here I was very careful about my choices, so then that way we could get nice whole numbers for the most part coming out of this. At least in terms of when sine and cosine are 0. Okay, we're going to graph this as best as possible. This is y1, this is y2. All right, so when I plug in 0, we're going to get 1. We're going to get 0 here. So I'm going to dot these points, and so this is 1, 0. When I plug in pi 12ths, I'm going to get 0 and e to the negative pi 12ths, which is roughly 0.769. So slightly less than 1. So 0 and 0.79, sorry, 769. And then the next value that we're going to get is negative e to the negative pi 6 and 0. And then we're going to get 0 and negative e to the negative pi force, which is around a third. And then at this very last one, we're going to get e to the negative pi thirds and 0, and this was around 0.2. So if we were to draw our trajectory, we start seeing this nice spiral occur, and it actually would continue, and this is the direction of travel, towards the origin. All right, again, this is starting at 1. So this is an example of a phase plane trajectory. So we have seen this before. So we can use this to gather information about the behavior, especially if we do have a solution. All right, so using the phase plane. To help gather information, we're going to denote our variables a little bit differently. So instead of using y1 and y2, we're just going to simply go as x of t, that's going to be our y1, and y sub t, this will be y2. So then that way, we look at this as x prime is equal to f of xy, and y prime is equal to g of xy. So now, if we think about it, the phase plane is just now the xy plane. So it makes life a little bit easier because we're used to dealing with the xy plane when we're graphing. All right, so now when we talk about x, we're talking about y sub 1, and when we talk about y sub 2. So the point x of t, y sub t is referred to as the solution point. All right. If the solution point corresponds to the equilibrium point, the components of x sub t and y sub t are constant for all values c. This point is also called, equilibrium solution. I got ahead of myself. The point is often called the equilibrium point. Often so much that I got ahead of myself. And the curve traced out by the solution point is called the solution curve. So that just getting our terminology down. So this is great if we can explicitly find the solution of our particular differential system. But is there a better way? And we have seen this better way before, so I asked this kind of with previous knowledge, and you've got the previous knowledge too. We can deal with direction fields to talk about the qualitative information without actually having to solve the system. So that's the great part. But how do we relate it to these guys? And so this is going a little bit more in depth of what a phase plane direction field is. All right. So here we're going to deal with vectors because we are dealing with the system of linear equations and matrices. So the vector v sub t is equal to x prime of t times the vector I plus y prime of t times the vector j. This is tangent to the solution curve at the point x of t, y sub t. So here I want you to imagine, if you will, imagine that this point x of t, y sub t, to kind of help better illustrate this, as an object moving along the solution curve. Then the vector v sub t is the velocity vector and points in the direction of instantaneous motion at time t at time t. So that's what the vector is actually talking about, is the direction and, if you will, velocity. So that's what velocity is. So that's where we're getting at. Now suppose that we select some arbitrary point, x bar, y bar, in the phase plane. So it might not be on this particular solution curve, but it could be on some solution curve. All right. Assume that a solution curve passes through. So it is a solution curve. So it doesn't have to be the specific one that we just found, but it could be any curve that is a solution that passes through this point at time t is equal to t bar. So again, t bar is going to be with x bar, y bar. That is to say, x bar, y bar is equal to the functions, or the values, x of t bar, y sub t bar. So that's where those guys are coming from. So at the point, this arbitrary point again, the velocity vector is given as v bar is equal to x prime t bar sub I plus y prime of t bar of j, or times j. And for us, this is just f of x bar, y bar. So I plus g of x bar, y bar times j. So what this really boils down to is just by evaluating the two right-hand sides of our system, and our system again was x bar was equal to f of x, y, and y bar, prime is equal to g of x, y, at our particular arbitrary value, we can find out the direction of the motion of the solution point at that point, x bar, y bar. So to help us with that, there's got to be, we know from vector calculus that the slope of the tangent line to a solution curve at x bar, y bar is simply m is equal to g of x prime, or sorry, x bar, y bar over f of x bar, y bar. Again, these are the derivatives of the functions x and y. Okay. And here, just to be careful, now we are going to find out what it means when f of x bar, y bar is equal to 0. We're actually going to talk about that here right now. All right. If f of x bar, y bar is equal to 0, and g of x bar, y bar is not, there's a vertical tangent line at that point. If both vanish, meaning both go to 0, so I equal 0, then x bar, y bar is an equilibrium point. So now we're tying that back in. And that should make sense. If that causes both to go to 0, then obviously we're dealing with the equilibrium point, because the idea of an equilibrium point is to make the whole system equal 0. So let's look at this particular pendulum problem, or not pendulum problem, just this particular problem now. And we're going to graph the phase plane here in just a little bit too. So determine the velocity vector at each point, 2, 2, and 1/2, 3/2 for the system. Okay. So our solution here is very straightforward. Part A, I want to look at f of 2, 2, and g of 2, 2. So when I plug in these values, what am I going to get? So I'm going to get 1/2, 1 minus 1/2 times x, which is 2, minus 1/2 of y, which is 2, all times 2. And if we simplify this, we're going to get negative 1 out. All right, same thing. We're going to plug this into g, which is our y function here, or y prime function. 1 minus 1/3 times 2, minus 2/3 times 2, all times 2. And this is going to give us negative 1/2. All right, so our velocity vector is equal to negative I minus 1/2 j. And since both are negative, the arrow that, or the tangent line would be going in the down and to the left. Okay, and again, remember what we did back in section 4.5 through 4.7 when we talked about the phase plane. These values, if they're both negative, it's going down and to the left. The slope would be positive, but the direction of travel is down and to the left. For part B, f of 1/2 and 3/2, you will find that we get out 0, and g of 1/2 and 3/2 is negative 1/16. Here, the velocity vector is equal to negative 1/16 j, which means that it's a vertical tangent line that we just talked about, and it points in the downward direction. Okay, so now we're going to incorporate more pieces of this to talk about phase plane direction fields. So, a phase plane direction field, we can construct a phase plane direction field by choosing a dense grid of sample points. So again, we know we can find for any point x bar, y bar, we can find out its particular vector velocity, or velocity vector. And at each point, we're going to draw a small arrow directed along the velocity vector, and that's it. So one thing that we do have to be careful of is if every arrow, how much space? Okay, just checking how much space I had. If every arrow is of the same length, or is drawn of the same length, this is referred to as a direction field. If every arrow is drawn so that their lengths are proportioned to the speed at that point, this is referred to as a vector field. which would be great if we said, okay, well, let's just use vector fields because then we can see the intensity of everything. But there's a problem with that. Vector fields sometimes lead to information overload because if you think about points near each other, and we're talking about their relative speeds at that point, you may have intersecting arrows, which visually can be distracting on or confusing when you're trying to figure out, okay, if I drop a point here, what does the curve look like? So that's the bad thing about vector fields is if you have so many points together and we're drawing with proportion to their speed, we could have intersecting lines which can throw our visuals off when we're looking at it. However, with the direction field, we can say, okay, here's all these points, they all have the same length, we're good to go. Bad thing is we can't see the level of intensity that they are speeding up or whatnot. So that can cause issues as well. So putting it all together, we can develop a less detailed phase plane picture that displays the essential features of the system's behavior. And so one thing that we're going to do with this is we are going to introduce the idea of null clines. Now we've talked about these before, but we called them isoclines when we're dealing with the direction field of a scalar differential equation. So again, scalar means that we're dealing with one equation instead of a system. All right. So these are where, so a null cline is where one of the right side functions vanish, meaning go to zero. So the cool thing is equilibrium points can occur only, I'm going to underline that, at a place where two null clines intersect. The key word is can occur. So not every intersection point leads to an equilibrium point. So be careful of that. So I'm going to underline can as well, just to emphasize this. So let's look at a particular graph. We're going to go back to our system that we were dealing with before. I did leave a lot of room just in case I over-explain things. So that's where we're going to head out to. So here's our example. Again, x bar is equal to 1/2 1 minus 1/2 x minus 1/2 y, all times x. Y bar is equal to 1/4 times 1 minus 1/3 x minus 2/3 y times y. An important note here is note f of x, so this is talking about our top function here, vanishes at x is equal to 0, and when this interior function goes to 0 as well, and that's when x plus y is equal to 2. So really simple, we just set this interior equal to 0 and solve. And that's where this expression is coming from. Likewise, g of x vanishes, g of xy, sorry, at y is equal to 0. And if we solve this interior for equal to 0, at x plus 2y is equal to 3. So what's cool here is we can gather enough information so we know an equilibrium point then is 0, 0. And then if we can find out the commonality between these two, so if I plug in 2, 0 into this, I will get out another equilibrium point because the 2 will cause this to go to 0 for x1 or x prime, and then the 0 will cause the second function to go to 0, and then also at 0 and 3/2 and 1, 1. These are all equilibrium points. for the system. So our null clines have been identified as x is equal to 0, y is equal to 0, and then these two linear equations. So let's graph that. All right. So I'm going to try to do these in black. So x is equal to 0 is a vertical line. All right. So there's one of our null clines. Y is equal to 0 is a horizontal line here. All right. So we've kind of gridded off our x-axis and y-axis for that part. And then we can rewrite this as y is equal to negative x plus 2. So at 0, 2 is this point. So this is our graph through here. This is one of our other null clines. Let's see, I'm going to do a small eraser here. All right, and then the other line is at 3 halves. Negative 1/2 x, 3 halves. Again, trying to draw as best as possible. If it doesn't happen, that's okay. All right, and so we can see here where our equilibrium points occur. We did say at the origin. We said at 2, 0. We said at 0, 3 halves. And at 1, 1. Notice that here and here, equilibrium points did not occur. And that's okay. Again, because equilibrium points only occur at the intersections, but don't necessarily have to occur at those intersections. So again, not every intersection point leads to an equilibrium point. However, the opposite is true, is every equilibrium point leads to an intersection point. So that's the nice thing, is you can identify a couple things from that. So what this does is it kind of grids off a little bit for our phase plane. Again, in a more simplified form. So let's look at this. So the signs of F and G determine the orientation of the direction field. So I'm going to cordon this off. So I'm going to say this is 1, 2, 3, and 4. So those 4 quadrants. All right. So in quadrant 1, F is greater than 0, and G is greater than 0. This means these arrows are going to be going up and to the right. Number 2, F is greater than 0, and G is less than 0. That means these are going to be going down and to the right. Number 3, F is less than 0. So again, the numbers are represented the quadrants that they're in. So in this quadrant here above 1, 1 and to the right, here G is also less than 0. So these will have a positive slope, but they're going to be going down and to the left. And in quadrant 4, f is less than 0, and g is greater than 0. So these are going to be going up and to the left. So if we were to draw, just to kind of get a basic idea of what these graphs are pointing at, so this is going to be pointing up in that quadrant. In quadrant 3, these are going to be pointing down. In quadrant 2, these are going to be pointing to down to the right. And in quadrant 4, these are going to be going up and to the right. All right, well, what about on those null clines? Well, we talked about if they disappear or what happens if they vanish. So along the null clines, the arrows are either horizontal or vertical, and their value is going to dictate which direction of travel. So on the particular null clines, x is equal to 0, f is equal to 0, which means that we are going to have vertical. So let's do these in red. So we're going to have these red arrows. And that's when g is positive. When g is negative, they're going to be pointing down. On y is equal to 0, g is equal to 0, but f is not. So these are going to be pointing to the right, depending on if they're positive, and to the left if they're negative. Likewise, on these lines here, y is equal to negative x plus 2, and y is equal to negative 1/2 x plus 3/2. We end up having these vertical lines pointing down. Or pointing up, depending on if g is positive or negative. And then horizontal lines pointing to the left or pointing to the right, depending on the sign of f. So this is how we can get a very quick idea of these solutions. So if I plot any points here, notice if I plot a point into the area of 1, notice it's going to be pushing it towards the equilibrium point 1, 1. If I plug a point into 3, it's going to push it towards the equilibrium point 1, 1, or depending on if I put it a little bit closer, depending on where I draw it. So notice that eventually everything is going to lead towards the center here. If I plug a point into 4, depending on where I plot that point, if I do it below the x-axis, then it's going to fall towards 2, 0. If I put it above the x-axis, it could lead towards the equilibrium point 1, 1, which are solution points. All right, so this is going to wrap up section 6.2, which is, again, equilibrium solutions and phase plane. So again, this is just a way to get behavior of solutions without actually having to graph the particular, or without actually having to solve the equations, which is really interesting. All right, y'all have a wonderful day, and then we're going to get to our last lecture, which is 6.4.